Hi, my name is Nicholas Pfeiffer.
Hey, I'm Mason Herrera.
My name's Aaron Safong.
We're doing the Sound Level Meter project, and here's some background. This project is a sound level meter using an STM32 and an analog sound sensor. Provides two visual indicators, the decibel readout on the OLED, and as well as a rising bar to detect volume level uh, on a LED strip. Both of these are used to showcase uh, like Both of these are used to showcase the level of sound, and the LED light strip lets you know if it might be too harmful if you don't have a measure on how loud, like 130 decibels is. Some Yeah.
And then for the components, we are using the Adafruit Max 9814. It's an electret microphone with a built-in automatic gain amplifier. And then we also have the Adafruit Pi OLED screen, and as well as a 144 LED strip connected to an STM32 board. And then we just have a generic button added to it.
And here's our showcase video of our project working live in lab. There's an OLED display reading out. You can see the LED strip reading the volume level, and in the corner we do have a live readout on a phone to compare the decibel value to.
Then essentially the block diagram, you can see all of our uh, devices connect to our STM32. So we have the main input, the audio sensor, and then we have the push button, which logs the max value once pushed. And then we have two outputs, one being the OLED display, and then one being the LED strip.
Here's our state machine diagram. Our goal is to pretty much have two states this device lives in, one state being just a live readout. So basically, it's constantly updating the OLED screen and the LED strip with whatever decibel value the sensor is reading. And then once the button's pressed, it'll go into a max log state. It'll stay reading for 5 seconds, and it's just going to record the loudest or the highest decibel value it reads. And then after those 5 seconds, it goes to a state of just displaying that value on the LED strip and the OLED screen, and it'll hold it until you push the button again, and then it'll go back to state one, which is just the live readout.
And then for the sound capture and tuning, as I said before, we're using the Max 9814. Um, it is a microphone, and since sound waves are AC, the measurement needed to be captured with a peak-to-peak value. We did calibration with an iPhone and a Fluke 945 sound meter as reference. We calibrated um, our software with a 50 decibel noise floor.
Whoops. For the OLED, we have an Adafruit 128 by 32 Pi OLED. As Aaron mentioned earlier, it uses I2C to interact with the STM board, and then you also are not required, but it is very helpful to have additional libraries used to fill in individual pixels and actually write the characters on the screen. This photo is showing a readout of the raw voltage level gathered from the electret microphone, but in the project it is converted to decibels to make it a more readable format. Uh, this In the code, it requires the variable pass from the ADC output of that microphone I had said earlier.
And for our other visual indicator, we incorporated a LED light strip. So the main functions for it were to have a gradient scale from green to red based on how loud the value being read was. And that was just split between green, yellow, and red. So it was split into thirds. And then as the value increased, it was scaled with the number of LEDs we wanted to light up. So obviously, with the sound being louder, more LEDs would light up. So that needed to be incorporated into code, and we are able to talk to this guy through pulse width modulation. We used one of the timers on channel one on the board and played around with clock signals until we got it right. And then the other feature was the max value log mode. Basically, as explained earlier, we used a GPIO input and we sent a high signal to it with the button to trigger that max value log state. So it hangs out there for 5 seconds and then outputs the max value.
One of the test cases we used was we used the sound meter to test the idle noise from the FSA team on campus. We also compared it to a Fluke analog decibel level meter. We then also compared it to a iPhone app sound meter, and that allowed us to tune the ADC output to be relatively accurate. For the third test case, we ran it through the max lag case to essentially ensure that there weren't any cases where the code broke or the log function wasn't reading out correctly, all to ensure reliability.
Overall, this project required modifications past the tutorial stages of what was taught in lab. It really made us understand what was going on with coding and the STM systems. We had a lot of issues with debugging and integrating our code. So that allowed us to work as a team to figure out what the issues were. We used Google and other sources to figure out, how to fix things, how to troubleshoot. And in the end, we had a full integrated system. We all came together as separate people coding different devices, and we all integrated into one final project.